This presentation will focus on projections. Now, the reason why this is important when it comes to GIS. Projections, everybody, is a manner in which you take, well, for the most part, a spherical surface and try to flatten it out. When you look at a map, okay, there has to be some way of flattening that map out. And by the way, projections are mathematical in nature. That is, when you create a projection, you can tell somebody on the other side of the world what kind of projection it is and how to do it by presenting them the mathematical equation as to how that was done. So again, taking that spherical surface and we're trying to flatten it out. So there's a way to do it. Now, when it comes to projections, another term that is going to be used quite a bit in this presentation is coordinate systems. Now, with a projection, again, you're trying to flatten out that spherical surface, and you're trying to do it in a mathematical way. But you're going to see that you're also going to be affecting coordinates along the way. Or at least it is going to be a part of this this process. Coordinates is the manner in which you identify locations, and so that is going to be another part of this. Well, this flattening out process, and also trying to figure out where things are located. Now, for the most part, when it comes to identifying locations, everybody, the world is pretty familiar with latitude and longitude, and that is a fine system. However, though, everybody, just that there are other ways of identifying your location. What we call a Cartesian system, using X and Y coordinates. And well, just think about back when you were in public school and you were working with the famous 4 quadrants where you had X and Y and positive X, negative Y. That's really what we're going to be dealing with here. So let's take a look at these a little bit more closely. Okay, now with the Cartesian coordinate system, what we're looking at, everybody, is we're sort of already looking at things in terms of already being flattened out. There's kind of an assumption of flatness. And you're going to see that there is a point of origin. There's going to be kind of that, again, when you look at the graph and you've got the X and the Y, the 4 quadrants, you're going to remember that there was the 0, 0 point. Well, you're going to find that in a Cartesian system also. And also, you're going to see with the Cartesian system that the more values that you're starting to add to the right, the decimal, you're going to see that, in essence, the accuracy starts to increase. And by the way, this is a very popular system, even though latitude, longitude, right on. I mean, that grade, it gets the job done. But you'll see there is some advantages to Cartesian systems. Now looking at latitude and longitude, again, this is usually the first thing that people learn when it comes to identifying locations on planet Earth. And well, for starters, what we're looking at that classical shooting angles from the middle of the Earth and the degrees to which you see represented on the surface. 60 being a very important number when it comes to latitude and longitude. And when it comes to longitude, you'll see that the prime meridian passing through Greenwich, England, is well, very important part of that system. And of course, represented verbally degrees, minutes, and seconds. Now in this graphic, you see the lines of latitude, longitude that are represented on the surface of the planet. As you can see, there are certain conditions. For instance, when it comes to lines of longitude, okay, the lines identifying the east and west of planet Earth, you'll see that as you get closer to the poles, all of a sudden you see a little bit of convergence there. So when it comes to with these spherical coordinates, identifying the distance between places, well, they're not 100% unified. I guess what the better way to put this is, you'll see just by looking at these graphics that there are times when lines converge, that the distance between lines of longitude, they seem to they get closer. Okay, so there's that. And now looking at the next graphic, here you see, for instance, when it comes to latitude that's being shown in this graphic here, you see that, okay, yeah, from the center of the Earth, if an angle was shot and if that was represented on the surface of the planet. That's what you're seeing right now when it comes to that value of latitude. Latitude, of course, looking at the northing and the easting. How far to the north, how far down to the south. And by the way, please catch it. If this happens, it's only human when this happens. Be careful. Don't say up and down, okay? Even though our good friends in Australia, they're referred to as the land down under. Well, I had the pleasure of visiting the Australian Embassy a few years ago in Washington, D.C., and the National Geographic Society created a map to where Australia was, guess what, well, if I use the term on top, well, it was at the very top of the orientation of the map. And there's absolutely nothing wrong with that. You can flip the planet, so to speak, and it is still perfectly legitimate. Okay, remember, in space there is no up and down. Now in this graph you'll see that the cartographers were having fun further representing the basis of latitude and longitude. And as I look at this, by the way, you're going to see, yeah, there's quite a bit these folks like to do with this sort of thing. By the way, when it comes to projections and coordinate systems, you could have an entire career just working with this stuff. So it is a pretty well-defined field. Now, when I look at this, I think of to the north of the equator. You'll see, well, I'm sorry, you don't see it, but what I see it in my mind, folks. There was a time in planet's history when people were navigating in the northern hemisphere. They would do what's called latitude navigation, and what they would do is they'd shoot an angle off of the horizon looking at the North Star when Polaris was in the sky, and you could pretty much get your degrees latitude in a primitive way, and that worked out pretty well. So there are ways that ancient mariners tried their best with the technology they had to navigate. However, though, when the sextant came into play, that's when really when it was the golden age of European exploration, when they finally were able to lock down better their location on the ocean, particular longitude. That's when well, that really great period of European exploration historically took place. Okay, now getting back to projections, the flattening of the sphere. Our planet is not a perfect sphere. It is a spheroid and a geoid. Now, what does that mean? What it means, everybody, is a spheroid. The Earth is actually wider along the equatorial zone, so it's not a perfect sphere. But also it's a geoid in that the distribution of mass on the surface of the planet is uneven. There are the Himalaya mountains, and in contrast to that, we could look at Death Valley in the United States below sea level. So there is this unevenness that's taking place. And this is going to kind of start getting into now, why are there so many different kinds of projections? Well, the reason for that is because you're going to see that when it comes to wanting to do, well, actually do functional things with the map, or, well, again, I don't want to steal my own fire without having the proper graphics in front of me. But just so you know that a projection is functional, and there are different strengths and weaknesses for each one of the projections. But let's start off by looking at the planet and knowing that it is a spheroid as well as a geoid. Now, when it comes to projections, you can start off by looking at things sort of at the grand scale of the flattening process. Now, what you're going to see here is a depiction of well, the sphere that we assume, of course, is Earth. Could be any planet, though. And here we have what we're going to call a cylindrical projection. And picture this now. Picture that you have a magical cylinder, and you somehow wrap it around the Earth, and within on the surface of this magical cylinder has like the ability to take images. Okay, it gets to take a scan of everything that is within it, and you'll see that you can actually, when it comes to the orientation of that cylinder, you can move it around too. You see in a graphic here in the middle versus on the right. Everybody here, you're looking at the different aspects, is what that's called. So looking at, number one, just how that surface of the sphere is viewed. Again, this is a cylindrical one. There are other ones too. The other two primary ones, conical, also called the dunce cap, and azimuthal, more of a sort of a flattened sort of orientate or view of the sphere. So you've got these primary projection, but again, the aspect is kind of the way it flips and rotates around. So looking at the cylinder, just try to imagine, okay, if it's at the beginning process of, so how are we going to flatten this sphere down to something that can be used on a piece, or converted into, say, paper or whatever for depiction. And so now going back to the question, finally answering it, why do you have all these different kinds of projections? Why not just have the projection, so that way the world is happy, everyone's on the same page? The reason for that, everybody, is because the Earth is a spheroid and geoid. There are inherent distortions whenever you take a spherical surface and you try to depict it as on a plane. Shape, area, distance, and direction, they are all going to be distorted to some degree. The question is, what are you willing to give and take? Now, if you were going to, say, for instance, fly a plane, when it comes to the kind of projection of the map that we would be using, distance and direction, most definitely, probably more so direction than anything, are of immense value. Okay, shape and area, the planet's surface, okay, you could live without that. However, though, if you are, say, looking at, well, you're into a real estate, and you're going to be purchasing large tracts of property and selling and so on and so forth, maybe shape and area would be more of a focus. But the bottom line is this. Here's the reality. You cannot have a map that is represented 2D that inherently there wasn't some distortion. It's going to happen. Now you're going to see in these examples right here, everybody, like for instance this Mercator projection. Well, in that graphic we were looking at when it came to primary types of projections, okay, this is a cylindrical projection. And so what that means is that there are inherent strengths and weaknesses when it comes to distortion. Or down the far right, you see that the one I mentioned before, in this methyl one. Well, you're going to see that it has this way of sort of focusing in on one particular area. And so distortion, as you move outwards, away, as you see the world here focusing on the North Pole, you'll see that. Well, look at Africa, okay? I mean, just like for instance, sub-Saharan Africa just suddenly gets squeezed together. So why do we do this, everybody? We do this, why do we know about projections and also inherently, of course, coordinate systems? Because there's going to be distortion. And so you got to ask yourself, when you're using GIS, okay, so now what is the main function of my project? What is it I'm looking at? Now, you're doing this, of course, because you have to make decisions about something while you're using the GIS, gathering information of some sort. Now, by the way, quite often, if you're at large scale, if you're in your local area, you'll be surprised at how much you can get away with when it comes to using different kinds of projections. I mean, the grand scheme of things, if you're just trying to figure out the general distance from, say, one state to another between two different towns, most generally used projections, you'll be just fine. However, though, there are cases where people use the wrong projections, and what's going to happen is there's going to be a distortion of the data. Now, a lot of people say, well, the GIS is just always going to compensate for this and that. GIS software does its very best, and it does a great job in many cases. But still, as a competent user of GIS, you have to be aware of the limitations of projections, and so that can be an issue. Again, depending, of course, on what tasks you have and the scale of the data, so on and so forth. Now, an example of distance distortion. Here you see a Mercator projection versus an Albert's equal area projection. And you can see that one of them, the United States, or at least the contiguous U.S. states, they look like they've kind of been, well, kind of flattened out by the Canadian border. And then with the Albert's equal area one, you see that, well, it kind of looks like the states have kind of started to be bent around a little bit. Okay, a little bit of an arc at the top between the U.S. and Canadian border there. But look at the distance for Mercator from L.A. to New York, about 3,100 miles. And then when we use an Albert's equal area projection, all of a sudden we get a value of around 2,400 or so miles. actual distance approximately 2,451 miles. This is a very good example. And so the bottom line is this: be aware of the projection that you use. And the internet, by the way, and as well as the ESRI software help option, you've got references there when it comes to the kinds of projections that you can use and their strengths and weaknesses. And also, of course, establishing coordinate systems when it comes to the measurement is of the location of place is also important too, which, by the way, you have the option to manipulate within the software. And let's take a look at an example right here. Now here we have an example of a UTM, Universal Transverse Mercator System. And by the way, this is a Cartesian system. One very big advantage of it is when it comes to distortion, it has a very unique way of sort of spreading things out, so to speak, when it comes to distortion. And this is a favorite of many militaries in the world. And one of the reasons for that is that if you're in a military and you're going to be reacting in different parts of the world, the question is, do you have a map library of those places? Let's put it this way: it provides more uniformity cartographically for an organization that is well, global in nature. Now, you might say, okay, so what kind of coordinate system are we looking at here? What are the units of measure? Okay, what am I going to see when it comes to if it's not latitude, longitude? Well, again, you're gonna have that Cartesian sort of XY solution, but also when it comes to units of measure, how many of you have heard of decimal degrees? Yes, you could actually use decimal degrees, which unless you're into cartography or global positioning systems, somehow is a part of your job. I defy most people on this planet to know anything about decimal degrees. And again, it's not because people are ignorant by nature. It's just they haven't had need to use that. So units of measure could be even set to feet if you want, or meters. So there is a lot of flex when it comes to how you identify location. And again, if you want to make this a full-blown career, it's there. Quite a few classes you'd be taking. Of course, the math is very important. You couldn't become good at establishing projection and coordinate systems unless you're good at math. But it is there, and it's a fascinating field. But just to summarize, everybody, in general, when it comes to projections, flattening out, okay, of a spherical surface, there are different approaches that can be taken, as well as when it comes to identifying location, you could utilize different kinds of coordinate systems too. So, as a good GIS user, you're just going to be aware of it, and just please keep in mind distortion, because that can haunt you. Thank you.